Hey, welcome back, ladies and gentlemen. We are going to talk about graphing exponentials and logarithms today. And I can already hear you guys complaining. Mr. Barton, you know my three greatest fears in life are graphing, fractions, and falling into a volcano and being burned alive from the feet up. But luckily, we're only going to have to deal with two of those three fears today. So you have an assembled Exodia, so there's nothing to worry about. So really today, what you want to learn is how to identify this stuff. Sorry, there's a fly in here. So if you guys hear something being murdered, it's the fly. Trust me, there are no dead people around. Every living animal except this fly is totally okay. But if you hear gunshots, don't worry about it. That's just me dealing with this fly. So you want to learn how to identify these graphs. And what that means is they're going to give you an equation, and you just have to go, oh, it's that one. You know, it's not going to be like you actually graphing something yourself. Although you could do that. It's not too bad. We're also going to take some time to talk about how do we transform these two types of functions. And we're going to start by looking at their parent functions. So we're going to start with the scarier of the two. Let's talk about logarithms, because this is the one that most of us probably don't have a real visceral understanding of yet. So what we're going to look at is this logarithmic function, and we want to just investigate it and kind of see what happens. So anytime I'm dealing with a new graph that I've never seen before, the first thing I'm going to do is just pick some random x's and y's, plug them into this thing, and kind of see what happens. Unfortunately, if I just want to pick random x's here, do you know what log base 2 of 3 is? If you said yes, you're probably a liar, because it's not a nice number. So because we don't really understand how to compute log base 2 of x, what we're going to do is we're going to turn this into the exponential, because they are literally the exact same thing. You can think of them as synonyms. They convey all the exact same information. One is just in log form and the other is in exponential form. So we're going to do that. So if I rewrite this in exponential form, my base is 2. Remember, logarithms tell us exponents. So the exponent is the y equals x. So this is just weird because we're going to pick y values, which is kind of backwards from what we usually do, and then we're going to go find x's. Usually we plug in x's and find y's, but you can do it the other way around. There's no rule that says you have to use the x as the independent variable. It's just the way most of the time you do it. So we can do 2 to pretty much any power we want, but let's pick some nice powers for y. So let's pick 0, 1, and 2. And just for the sake of checking them out, let's also look at -1 and -2. All right, so 2 to the first power, anything to the first power is just whatever the base is. So 2 to the power of 1 is 2. And I'm calculating this, I'm simplifying. 2 to the power of 1 equals x. So 2 equals x, right? So we're calculating the x by plugging in a y. I understand that this is backwards from normal, but it'll work out, trust me. All right, if we plug in 2 for y, 2 squared is 4. And if we plug in 2 to the power of 0, any number except 0 to the power of 0 is 1. That's going to be super important because this point is going to show up a lot for us. So it's important that we understand why this happens. When y is 0, anything except 0 to the power of 0 is always going to be 1. So 100 to the power of 0 is 1. -12 to the power of 0, that's 1. 0 to the power of 0, that's, don't worry about it. But everything else, it's 1. So we've got that weird one. Now let's think about what happens if we plug in these negatives. If we have -1, 2 to the -1 power equals x. For negative exponents, the way we handle this is we take the base and the exponent, move them to the denominator, and make the exponent positive. So what that would look like for us here is 1 over 2 to the first power is x. So x is just 1/2. Okay. If we do 2 to the negative 2 power equals x, that's 1 over 2 squared equals x. So that's 1 over 4. So if you haven't picked up on the pattern, these negative ones are pretty much the same as the positive ones. They're just the reciprocal. They're 1 over that number. Okay, cool. All right, I'm going to erase this just to kind of clean up my board a little bit here so we're not quite so distracted. Okay. All right, so now that I have some points, and keep in mind, these are the points for this logarithm. Don't mind that I used this exponential to get them. This exponential means the exact same thing as this logarithm. They're just two different ways of writing the same thing. Okay. So let's go graph these points. So we have a point at 1, 0. So there's one right there. We have a point at 2, 1. So right there. At 4, 2. Right there. And now we got to be careful with these. 1/2, negative 1. So I go over half, down 1. Then I go over 1/4 and down 2. So 1/4 is half of a half. So right about there, we're going down 2. So we have these 5 points, and we could plug in more y values to this if we want. We could do 2 to the negative 3, 2 to the negative 4. We could do 2 to the 4th, and so on. But what's going to happen is it's going to follow this curve. So let me fill in this graph. There we go. Not the best graph in the world, but not the worst. Okay, this is what a logarithm looks like. So let me kind of point out some of the key features of this graph that you want to know about, and then we'll go look at some other stuff. So the first one is this point right here is that point right there. This point should happen on pretty much every logarithm, and we'll see how it moves around a little bit once we get to transformations, but this 1, 0 point is common to most logarithms, as long as you don't take this thing and then like slide it around like this. As long as you don't horizontally or vertically translate it, you should get this point. And even if you do shift this thing sideways and up, that point will always be a reflection of those transformations. So we're going to use this to help us figure out some logs. The other thing I really want to draw your attention to is this log graph goes down and it keeps getting really close to the y-axis, but it will never quite touch it. So there's a word we have for things you get really close to but never really touch. They're called asymptotes, and I know you've heard that before because I told them to you. So there is a vertical asymptote for all logarithms. And the logarithms will get really close to that and then just diverge off to one side. They won't ever cross it, and you'll only ever be on one side of it. So it'll either be on the right entirely or on the left entirely. And we'll talk about where this comes from and how to find the equation very, very easily later. Okay, so this is what a log looks like. We want to be on the lookout for this 1, 0 point, and we want to be aware that there's a vertical asymptote that our graph is going to get very close to. All right, let's take a peek at an exponential function, and this is going to be a lot easier because it's the same function as this that we just looked at, but notice the x and y have just swapped positions here. So now x is the thing operating on the base and y is our output, again the way it should be. So this will be a lot more familiar to you. There is a word for when you just switch the position of x's and y's. It's called an inverse. And we did that at the beginning of the semester. We talked about function inverses, where I gave you like y equals 3x plus 2. And I said, find the inverse, and then you did x equals 3y plus 2, and then you solve for y. That's not a coincidence here, because the only difference between this exponential and this logarithm is switching the x and the y's. That's because exponentials and logs are inverses of each other. So you want to think about logs is like the division of exponents, right? Division is to multiplication as logs are to exponents, right? If we're doing the metaphors or whatever they're called in like 3rd grade, right? So logs and exponentials are in fact inverses of each other. So we're going to pick some random x's, and my random ones that I always choose randomly are -2, -1, 0, 1, 2. And then we've already plugged all these into exponents, so we know that this is 1/4, 1/2, 1, 2, and 4. So now we're going to graph these, and we're just going to get the inverse. So -2, 1/4, -2, 1/2, 0, 1, 1, 2, and 2, 4. So our exponential looks like, oh, that's ugly. I was doing so good here, and then I didn't keep that curve. It's all right. Nobody's perfect. So let's talk about the important stuff here. Again, we have this 1, 0 point, but now it's 0, 1. This is again a super important point, because if we change our base, that's not really the important part here. The important part is the x and the y. If this were maybe 3 to the power of x equals y, 0, 1, is still an ordered pair for this graph, because 3 to the power of 0 still equals 1. If this were 100 to the x equals y, 100 to the power of 0 still equals 1. So 0, 1 is still an ordered pair even if the base is 100. So regardless of what your base is, we should have a 0, 1 point on pretty much every single exponential graph, with the kind of like footnote unless you slide it up or down or sideways. Okay, so we want to just be aware of that point. It's super important. I don't know that it actually has a specific name, but it's in common for most of our exponential functions. The other thing I want to point out to you is there is a horizontal asymptote for all exponentials. We're going to want to know how to find where this thing is, but, excuse me, I'm sorry. But it's going to be pretty easy. It follows the same pattern every time, and we'll look in the same spot every time to figure out where this horizontal asymptote is. So for exponentials, on the left side, they continue to get smaller and smaller and smaller because we're plugging in smaller x values. This would be 2 to the -3rd is 1/8. 2 to the -4th would be 1/16, and so on. So our y value is going to keep getting smaller and smaller and smaller, but never quite reach 0. Meanwhile, if we go in the positive direction, as this exponent increases, 2 to the 3rd, 2 to the 4th, 2 to the 5th, our y values just continue to get bigger and bigger and bigger. All right, so there's the general outline of what they look like. Now let's go talk about our transformations. So before we start talking about these log equations, let's go just refresh our brain on transformations. So we have y equals a x minus h, we'll make it squared, but that's not really important here, plus k. So we have a coefficient in front that can stretch the graph vertically. You can take a graph that looks like that and then stretch it so that it looks like that. We can use our h value. Remember, this is our horizontal shift. And remember, our h value is always reversed. So if this says x plus 2 squared, even though the h looks like a plus 2, h equals -2 because this negative is part of the equation. And it's going to take us left 2, even though left on the x-axis is negative, not positive. So we need to remember the thing inside the function with the x is our h value. It's going to shift it horizontally and it goes the opposite direction. This k value is our vertical shift. And that's going to move us up and down. And whatever value k has, that's what you do. So if it says +3, you go up 3 just like it says. So for logarithms and exponentials, we have the same type of things happening. So you're going to have a base here. The base does not really affect your graph. What a base will do for your logarithm is if you have a graph, let me make a graph, sorry. And you have a small base. It might look kind of like this. If you make this base bigger, all that does is make this turn a lot more abrupt. So if this were 2, maybe that's the blue one. And if I change it to 4, it'll look more like that. And it'll level off a lot sooner. So the base just sort of squats out your graph, makes it a little shorter. But we're not going to change that a whole bunch. You don't need to worry about that kind of transformation. That's not really a thing that we're equipped to handle yet. Okay. The transformations you need to worry about are, we could have an a value, just like we have an a value here. And this will do the same thing. It'll just stretch out your graph by whatever factor that a value is. So if it's a 3, it'll make your graph 3 times taller. If it's a 1/2, it'll make your graph half as tall. Inside the logarithm, in the argument, you still have your -h, and this is still a horizontal shift. What's important here is this horizontal shift determines this vertical asymptote that we saw on our logarithm. So let's write that down because you want to remember that for the rest of your life. The asymptote of a log is x equals h. And now draw like flames on this or something. Maybe put like, I don't know, what else do you like to draw? Angry face. Here, let's make it an angry like cat. There, he's ticked that he has to learn logs. How? Anyway, the point is this is super important. You have to remember that for the rest of your life. Okay, this h still does horizontal shifts. So if we go look at our log, if I take this graph and move it right 1, this asymptote moves right 1 with it, and then your asymptote is now at x equals +1. So if you move this graph, the invisible line that gets really close to moves with it. So that's why the vertical asymptote is connected to your horizontal shift for your graph. Okay. And then, of course, we do have a vertical shift for logarithms. It shifts it up and down. One important thing you'll want to know is that when you shift it up, if you shift this up 1, your asymptote will still be at 0, but now your 1, 0 point would be at 1, 1 instead of 1, 0. So this point right here is a good indicator of, do I have a vertical shift? That'll help you find it if you can figure out where this point is. Okay, so A stretches that thing out, H moves it left and right, and tells you where your vertical asymptote is. That's important. And then K moves it up and down. I don't think it's on your homework, but just so you know, if you put a negative in front of this x, it will flip it horizontally. So if our regular log graph looks like that, if I put a negative in front of this x, the new log graph will look like that. So you can flip it horizontally. That'll work. But I don't think that's really an issue that you're going to have to worry about too much for your homework. All right, let's talk about transformations of exponentials. Let me make this a little bit bigger so it's easier for me to write on. All right, so this is your base. Same thing with bases of logs. This isn't really going to change. They're not going to say compare the transformations of y equals 2x to y equals 3 to the power of x. That's not a good transformation to have. This is not really something we want to worry about. Okay. All this does is if this is y equals 2 to the power of x, if you change your base to a bigger number, it just makes this a lot steeper. So it'll go like that. It won't be quite so like kinked. It'll be still rounded, but it just goes up a lot faster because it'll go 2 to the power of 1 is 2, then 4, then 8. For 3, it'll go 3, then 9, then 27, because powers of 3 just get bigger faster than powers of 2. So don't worry about your base so much. Of course, you can have an a value in front. That will stretch out your graph. One important thing to know is that if we have our exponential graph, this point that we're kind of aware of at 0, 1, if you take this and multiply it by, say, 2, it'll stretch this graph, and now it will be at 0, 2. So if this moves, it could indicate that we had a vertical shift, or it could indicate that we're stretching our graph with a coefficient. I think most of the time on your homework, though, it's going to do a vertical shift and not really mess around with these coefficients because it's hard to tell on graphs other people give you and stuff. So, okay, so we could have an a value, and it'll just stretch our graph. Now, this will also have an h value, but it will be in parentheses in the exponent with the x. This still does the same thing. This is still a horizontal shift. It's still reversed from whatever the sign is. So if you see 2x plus 2, that's left 2. And you're going that direction, in the negative direction, even though this says plus, because h is always backwards from whatever the sign is. Okay. And then, of course, you'll have k, except it doesn't go in the exponent. It's just a big number that you add at the end of your exponential equation. Okay. So now at this point, we're kind of aware of how everything works. Let's go look at some graphs that I made just so we can point out how things have changed while looking at the equations. All right. So the first one we have here is y equals log base 2 of x plus 1. So this plus 1 is our h value, but remember it is reversed from the sign it actually is. So h equals negative 1, and we're going left 1. We don't have a k value here, so it's not going to shift up or down. So we can see here at negative 1, there's our asymptote at x equals negative 1. That's the equation for the asymptote for this log. Our point that we want to watch out for are back that up. Our 1, 0 point has shifted 1 to the left, so now it's at 0, 0 right here. But it's still pretty easy to identify because it's made of integers. And that's really all you need to know about that graph right there. Because our base is 2, you kind of want to look out for powers of 2. So we go 0. If we go over 1, we're at 1, but 1 is 2 to the power of 0. Then if we go over 2 more, we're at 2. So we'll go 1, then 2, then if we go over 4 from there. So your powers of 2 will be on the x-axis. All right, if we look at y equals log base 2 of x, here we don't have a number added or subtracted to the x on the inside. So h equals 0, and we can see our vertical asymptote right there. What you want to do to find your asymptotes is just look at the tail of this graph and kind of see where it levels off at. So because h equals 0, our asymptote is at x equals 0 because our asymptote is always at x equals h. Okay. This plus 2 has moved the whole graph up 2. So you can see we don't have that 0, 1 point, or I'm sorry, that 1, 0 point. But if we go up 2, 1, 2, there it is. So that 1, 0 point is now 1, 2 because we've added 2 to the y values. All right. Let's look at some weird ones. On this one, I just threw a whole bunch of transformations on there so we can kind of see what's going on. But don't freak out. So let's break it down. Here's our h. So h equals positive 3 because it's always reversed from the sign you see. So our asymptote should be at x equals 3. Let's go look. There's 2. Right in the middle is 3. Yeah, it looks pretty close, right? It looks like it's getting there. So it looks like our asymptote is in the right spot. Usually, this point or this point is just 1 to the right of our asymptote. So let's go 1 to the right. Oh, it's not there. But we have this plus 2. So if we go 1, 2, there it is. And then this 3 has just curved our graph. It stretched it out. If we didn't have this 3 here, our graph would probably look more like that. It'd be a little flatter, but you don't need to worry about that. As long as we can find this asymptote and this point, we're probably good. All right. And then just so you guys can see it here, if you throw a negative in front of your x, it has flipped the entire graph horizontally. So it's flipped it this way. But we can see h equals 0 because we have nothing added or subtracted to the x inside the logarithm. And we can see we still have that vertical asymptote on the y-axis at x equals 0. So that's still there. We still have our point, except now it's at negative 1, 0. And that's just because we flipped the graph over with that negative sign. All right, cool. All right, let's check out some exponential graphs. So for exponentials, we have, again, the base, not super important. We don't have an h value here because there's nothing being added or subtracted to our x in the exponent. But we don't have a vertical asymptote for exponentials. They go left forever and right forever. But we do have a horizontal asymptote. This one we can see is at 1. There's the 1. So for exponentials, our horizontal asymptote is determined by k. Maybe we should write that down. For exponentials, the horizontal asymptote is determined by k, and it's actually at y equals k. That's going to be your asymptote for every single exponential. So because our k equals 1 here, we can see our asymptote at y equals 1. And then that point that we always look out for, this one is 1 above the horizontal asymptote, is still right there. Normally it's at 0, right, what you say, 1, but because we've shifted the whole graph up 1, this point got moved up 1. All right, looking at this one, we have y equals 2 to the power of x minus 2. So here's our h equals positive 2 because the sign is reversed, and k equals 0 because we're not adding or subtracting anything to the exponential term. So we can see our horizontal asymptote right there on the x-axis. The equation for that line is y equals 0, and we just get that from our k value. And then we can see we don't have our normal point at 0, 1 because we shifted this whole graph 2 to the right. So if we go over to 2, we can see our point right there. So it just got moved over, but we can still find it. All right. Here, I've changed the base to 3, so that's just curved this a little more sharply than this one. This one's nice and smooth. This one curves a little harder, but that's okay. So we have h equals 2, so we're going to shift our whole graph right 2, and then minus 5, so we're going down 5, and k equals 5. Sorry, excuse me, negative 5. The sign stays the same for k. So let's go check for our horizontal asymptote. Right here at negative 5, there's negative 4, negative 6, and negative 5's in the middle. We can see a really clear asymptote where that graph levels off. Normally we have that common point 1 above the asymptote, but because we're shifting right 2, 1, 2, it's been moved over. And we found our two important things, that common point and our asymptote. And then this one, again, I just threw the negative in front of the x to show you kind of what happens. But h equals 0, k equals 0. So we can see our horizontal asymptote is still at y equals 0 because our k value is 0. And that common point at 0, 1 is still there because we haven't moved horizontally or vertically. The only thing this negative does is it flips our graph over. The reason for that is because we could simplify this negative in an exponent. We could turn this into y equals 1 over 4 to the power of x. And we could even simplify that to 1 over 4 to the x. This isn't true for every single fraction, so don't try that on like 2/3. But because the 1 on top is a 1, it works out. So just be aware that this equal sign isn't true for every single fraction. It's just this is a special fraction. But, you know, that's just because I'm a math warlock. You know, like you can't expect not to have some cool math tricks if you're a math warlock. All right, so there's a bunch of examples. Hopefully this is kind of showing you the important stuff to be looking for, and we know how to see how far left and right is our graph going to move, where our asymptote's at. That's really the important stuff you need to know for your homework. If any of this wasn't clear, or you feel like you're not really understanding graphing all that well, make sure you ask me. And that doesn't mean you have to wait the 15 minutes I'm going to give you for homework, and then I'll ask for questions, and then you say, hey, actually, I didn't get any of that. You can say, hey, Barton, I didn't get any of that before you try the homework. You know, we can just skip the wasting 15 minutes of staring at stuff we don't understand. But, you know, you do you. Whatever works for you, I trust you. All right, have a good day, you guys.